Hello friends, welcome to Online Guru. Today's our topic of discussion is neurohumoral transmission in central and autonomic nervous system. First of all, I am going to tell you what is neurohumoral transmission. Neuro means something which is related to the nervous system and humoral means a chemical substance. What is the meaning of humoral? Humoral means a chemical substance which has been involved in the transmission of the nerve signals or nerve impulses from one neuron to another through the synapse or neuroeffector junction. This is what is called as collectively neurohumoral transmission. So in this neurohumoral transmission, let us see what is the exact definition of the neurohumoral transmission. It is a transmission of impulses through synapse or neuroeffector junction with the help of chemical substances called as humoral substances. It is a transmission of the impulses which is going to occur through synapse. If this is a one neuron and this is a second neuron, the gap which is present between the two neurons is called as synapse. And neuroeffector junction means the actual gap which is present between the neuron and the effector organ. If this is a effector organ, this is a neuron, the gap which is present between the effector neuron and the last neuron, it is called as the neuroeffector junction. Okay, and how it is going to release, how there is a transmission of nerve impulses from one neuron to another. It is due to the presence of a chemical substance called as neurotransmitter, and this neurotransmitter is a chemical substance, hence it is called as a humoral substance. Here it is a acetylcholine. This acetylcholine is a neurotransmitter which is a humoral substance, which is a chemical substance involved in the transmission of nerve impulses, nerve signals from one neuron to another neuron. This process is called as neurohumoral transmission. You can see in the diagram, this is a myelinated neuron and this is a gap which is present, which is non-myelinated. It is called as nodes of Ranvier. What will happen? The electrical signals are going to pass through nodes of Ranvier from one node to another node. Okay, due to the presence of myelinated neuron, myelinated sheet, which is going to act as an insulator, which is not going to allow the transmission of electrical impulses from it, but the nerve impulses are going to carry through the nodes of Ranvier. Okay, which will increase the speed of the nerve conduction. This process of the it is the process of travel or propagation of the nerve signals or impulses within the same neuron is called as impulse conduction. You have to take a note of it that when there is travel of the nerve impulses within the same neuron, this process is called as impulse conduction. But when there is a transmission of nerve impulses from one neuron to another neuron, this process is called as impulse transmission. There is a difference between conduction and transmission of nerve impulses. And this is a neurotransmitter. This neurotransmitter is a humoral substance. Here it is acetylcholine, which is going to help in the transmission of nerve impulses. We are going to actually see the steps which are involved in the neurohumoral transmission. Okay, first of all, I am going to tell you what is impulse generation. Before going to it, we will see what is the actual mode of transmission of the nerve impulses. It is a passage of the impulse. Impulse means any signal. It may be in the form of electrical signals which is going from one neuron to another. Either the impulses will move from one neuron to another neuron, or from directly it can go from one neuron to effector organ. This is what is called as neurohumoral transmission. There is transmission of nerve signals with the help of humoral substance. Humoral substance is acetylcholine, which is a neurotransmitter. We are going to see now the steps which are involved in the neurohumoral transmission. The first step is the impulse generation. Means here the actual nerve impulse is going to get generated. We are going to see in detail how it is going to get generated. Second one is the transmitter release. There is a transmitter, that is neurotransmitter, is being released in the synapse or neuroeffector junction, which is going to allow the carry or transmission of the nerve impulses. Third one is the transmitter action on postsynaptic receptor. Means what will happen? There is a release of the chemical substance or nerve impulses are being released, or the neurotransmitter is being released, and which is going to act on the postsynaptic receptor. Then when the neurotransmitter is going to bind to the postsynaptic receptor, it is going to show its activity on the effector organ. Then finally it is the termination of the transmitter action, means the neurotransmitter which has been released in the synapse or neuroeffector junction, it has been degraded or it has been reuptake, means it is going to again go back to the vesicles. The substance which are present within the vesicles are going to go back to its pre-ganglionic neuron. This process is called as termination of the nerve impulses or transmitter action. The first step is the impulse generation. How the impulse or nerve signals, electrical signals are going to develop. We are going to see in this slide. First of all, I am going to tell you when there is any resting membrane potential. Suppose this is a cell, there is no any impulse generation, it is in the resting membrane potential. At a resting membrane potential, normally the nerve cell, we are going to speak about nerve cell, not a cardiac cell. In the nerve cell, the resting membrane potential is slightly towards negative polarity. It is negative side. It is having negative polarity. The actual voltage is minus 70 millivolts. This is the actual electrical potential of the nerve cell normally at a resting state. This is called as resting membrane potential. When there is any nerve impulse which is going to come towards this cell, suppose this is a cell, okay, when there is any transmission of nerve impulses is going to hit this cell, okay, this is a nerve impulses, it is going to come to this side. What will happen? There is stimulation or electrical impulses are going to travel to the nerve fiber. This is going to get stimulated, and what will happen? There is opening of the sodium channels. This is the sodium channel which are going to get open, and the stimulus or the electrical impulses arrive to the nerve fiber. Means this neuron, the nerve impulses, if this is a nerve cell, it is this electrical impulses are going to come and strike this nerve cell. And what will happen when the nerve cell is going to get stimulated? There is an opening or influx of the sodium channels. These sodium channels are going to get open, and this sodium which is present outside the nerve cell is going to come inside the nerve cell. Means when the sodium, which is a positively charged ion, it is a cation, it is going to come from outside of the nerve cell to the inside of the nerve cell. It is going to increase the positive polarity inside the cytosol of the neuron, that is neuroplasm. Then what will happen? It is going to ultimately cause slight increase in the positive polarity up to 20 millivolts, okay, plus 20 millivolts. Then what will happen? First of all, I am going to tell you this sodium channels. First of all, when this nerve impulses are going to arrive directly, it is not going to activate voltage gated sodium channels. No, the voltage gated sodium channels are not directly going to be activated by the nerve impulses, but these nerve impulses are only going to trigger very slight opening of very normal mechanical operated sodium channels. This mechanically operated sodium channels are going to get opened when there is any nerve impulses which is going to strike the nerve cell. Upon the activation of the, when the sodium ions are going to come inside through the mechanically operated sodium channel, there is change in voltage, and due to the change in voltage, the voltage gated sodium channels are going to get open. If this is a mechanically operated sodium channel, this nerve impulse is going to strike this nerve cell and going to open this mechanically operated sodium channel, which is going to cause influx of the sodium, but this sodium is not sufficient to cause depolarization, but this sodium is only going to trigger the opening of the voltage gated sodium channels, and this voltage gated sodium channels are many in quantity, many in concentration. When this voltage gated sodium channel are going to get open, there is a huge surge, huge concentration of influx of the sodium from outside of the nerve cell to the cytosol of the nerve cells, leading to increase in the positive polarity inside the cytosol of the nerve cell to plus 20 millivolts. We are seeing here, due to the opening of voltage gated sodium channels, leading to huge surge of sodium influx, which will increase the positive polarity up to plus 20 millivolts. Then what is going to happen further? Now, till now we have seen opening of voltage gated sodium channels is going to cause huge influx of sodium inside the cytosol. The membrane polarity will go till plus 20 millivolts. Now what is going to happen? There is opening of the potassium channels. there is a opening of potassium channels, through which the potassium which is positively charged are going to move from cytosol of the cell, that is inside of the cell, towards outwards of the cell, that is in the ECF of the neuron. Then what is going to happen? The positively charged cations, that is so potassium, is going to move outwards. Hence there is a decrease in the positive polarity and increase in the negative polarity. The sodium channels will close after some time. Now voltage gated sodium channel are going to come inside. Okay, it is going to open and the sodium will come inside, and ultimately there is increase in positive polarity, that is plus 20 millivolts. Along with it, after some time there is opening of potassium channels and sodium channels are going to get closed. Means sodium is not coming inside, but potassium is moving outwards. Means now there is no any positive ions coming inside, while the potassium ions which are positive are going outside. Then what is going to happen? There is decrease in the positive polarity and increase in the negative polarity into the cytosol of the neuron. Then what will happen? The potassium is still moving out due to the prolonged opening of potassium channels. Now what is going to happen? The membrane which achieved depolarization. Depolarization means there is a polarization, there is a decrease in the negative polarity, there is an increase in the positive polarity due to the opening of voltage gated sodium channel, due to the more positive ions accumulated inside the cytosol of the cell. But when the sodium channels are going to close and potassium channels are going to open, sodium will not come inside, but potassium are going to move outwards. Hence the depolarization is not going to remain still further. Now it is a time that the cell is going back to the repolarization. Means again it is moving towards a negative polarity due to the closing of sodium channels and opening of potassium channels. Now membrane will become more negative due to the loss of potassium from inside to outside, and further potassium influx is going to cause hyperpolarization of the neuron. Hyperpolarization means excessive polarization, excessive increase in the negative polarity inside the cytosol of the cell, because there is no influx of sodium is not coming inside, positive charge is not coming inside, while negative is moving outside. Hence it is further going to cause hyperpolarization. And now the action potential is been generated. Again there is a further nerve impulses is going to come on, and it is going to operate, it is going to trigger mechanical operated sodium channels, which is going to cause influx of some amount of sodium. Again this sodium is going to cause change in the voltage. Further it is again going to trigger the voltage coated sodium channel. Again there is a depolarization phase when it is going to achieve the threshold potential. In this way the cycle is going to continue across, and there is a neurotransmission, that is impulse transmission, which is going to take place. This process is called as impulse generation. In this process the impulse is being generated, the electrical impulses, that is electrical signals, are being generated. Let us see with respect to diagram. Now this is a resting membrane potential of minus 70 millivolts. When there is any nerve impulse which is going to come, it is going to cause opening of the sodium channel. This sodium is going to come inside, increase a slightly positive polarity. It will trigger the change in the voltage, and finally it is going to cause the activation of voltage coated sodium channel, which is going to cause huge concentration of sodium to enter inside the cytosol from ECF, leading to achieve the threshold potential. This threshold potential is the maximum potential at which the actual depolarization of the cell is going to take place. When there is a threshold potential which has been achieved, there is a depolarization, means the membrane inside the neuron is going to become slightly positive. Okay, that is less negative. Then what will going to happen? There is a increase in the positive polarity. Again at this point the sodium channel are open, but at this point sodium channel are being closed and potassium channel are going to get open. Due to the opening of potassium channel and inhibition of the closing of the sodium channel, there is a no any influx of the positively charged ions, no influx of sodium, and hence what is going to happen? Influx of potassium is going to take place. Finally the actual graph is going to come down. There is a again decrease in the positive polarity and increase in the negative polarity. Finally it is due to the potassium efflux. This phase is called as repolarization. Again there is increase in the negative polarity. Finally there is a phase of hyperpolarization where sodium channels are already closed but potassium channel is still open, which is going to cause further decrease in the membrane potential, or there is a further increase in the negative polarity leading to hyperpolarization of the membrane. The membrane will become most of the negative, that is hyperpolarization. and finally again it is going to come back to the normal state, and again there is an impulse conduction which is going to take place across the neuron. This is how this process is called an action potential, which is going to take place inside the neuron. Then we are going to see the action potential in the neuron. Normally, at the resting membrane potential of the neuron is minus 70 millivolts. At a resting phase, when there is no any new nerve transmission or nerve impulses, when there is no any nerve signals, nerve impulses, the resting membrane potential at rest of the neuron is minus 70 millivolts. That is, it is more negative inside the cytosol, and no influx of sodium is going to take place. All the sodium channels, irrespective of its whether it may be mechanically operated sodium channel or voltage gated sodium channel, all are closed. And also there is a efflux of potassium is still open. Okay, note it. At resting membrane potential, why resting membrane potential is going to be maintained minus 70 millivolts? Why it is negative polarized? Because when sodium channels are closed at this moment, still the potassium channels are opened in less quantity, which is going to cause leakage of potassium ions constantly even at resting membrane potential through the potassium leaky channels. I am not speaking about voltage gated potassium channels. See, note it down. I am not telling at resting membrane potential the potassium voltage gated potassium channels are not open, but the potassium leaky channels are open. This is a very fine channel through which the potassium, excess of potassium are going to leak from cytosol to the ECF. Now it is going to maintain negative polarity due to efflux of potassium due to loss of positive ions inside the membrane, that is minus 70 millivolts. Then when there is any stimulation or distortion of the nerve cell due to the any electrical impulses or mechanically operated sodium channel are going to get open. I have told you, when any electrical impulses are going to come, when there is any mechanical distortion which is going to happen, there is initially opening of mechanically operated sodium channels. This is going to cause very less amount of sodium to come inside the cytosol. Finally, due to this less sodium concentration which is coming from ECF to ICF inside the cytosol is going to trigger the change in voltage and increase the positive polarity slightly, which is going to trigger the opening of the voltage gated sodium channels. Okay, this mechanically operated sodium channels are already open, and membrane potential becomes some less negative. Membrane potential is going to become some less negative due to the opening of mechanically operated sodium channels, which is going to trigger the opening of voltage gated sodium channel. See, when voltage gated sodium channels are going to get open, when this mechanically operated sodium channels are going to cause influx of sodium, and when this sodium concentration is going to reach up to a threshold means the concentration at which there is enough concentration of sodium to trigger the opening of voltage gated sodium channels, and hence at this threshold potential the voltage gated sodium channel are going to get open, and there is a huge influx, a huge surge of sodium which is going to come inside the cell, which is going to cause decrease in the polarity of the cell. This process is called as depolarization of the membrane. The membrane will go towards more positive side, it is plus 20 millivolts. Now afterwards it is going to reach towards a certain height. Okay, the sodium gated channels are going to close after a moment, after some point of time, and potassium voltage gated potassium channels are open. Previously it was leaky channel, but now it is a potassium voltage gated potassium channels. Now sodium is not coming inside, but potassium is going to open. Voltage gated potassium channels are open, which is going to cause efflux of potassium from inwards to outwards of the neuron. Means there is again the increase in negative polarity due to loss of cations, due to loss of potassium. It is going to cause increase in negative polarity. This phase is called as repolarization of the membrane. It is due to the loss of calcium and no influx of sodium. Further, when there is excessive loss of potassium through the voltage gated potassium channel, and this process is been prolonged, it is going to cause hyperpolarization of membrane. Finally, the nerve impulse is conducted from one node of anywhere to another. You can see if this is a node of anywhere, the impulse transmission is going to take place like this, because here it is myelinated sheath. which is not going to allow, it is going to act as an insulator. It is not going to allow transmission of electrical impulses. Hence, the electrical impulses are going to jump from one node of anywhere to another so that it can increase its speed. And this process is going to occur in the same neuron. This process is called as neuroconduction. Then we are going to see actually how the neurotransmitter is been released. Normally, neurotransmitter is stored in the vesicles. There are some vesicles in which the neurotransmitter is been stored. These vesicles are present in a presynaptic or preganglionic neuron. Okay, the neurotransmitters are of two types mainly. First one is the excitatory neurotransmitter, which is going to cause excitation in the neuron, and second one is the inhibitory neurotransmitter, which is going to cause inhibitory effect on the neuron. This excitatory and inhibitory neurotransmitter, if this is a excitatory neurotransmitter and this is a inhibitory neurotransmitter, they are stored in the vesicle. This is a vesicle which is present within the neuron. This is a neuron or nerve cell. They are stored in a presynaptic. This is a presynaptic vesicles. Presynaptic nerve. These are presynaptic nerve and these are the synaptic vesicle. This circle is called as synaptic vesicle, in which there is a presence of excitatory as well as or inhibitory neurotransmitters. And these synaptic vesicles are present only in the presynaptic or preganglionic neurons. Okay, then what is going to happen when any nerve signal is going to trigger? It is going to come from one axon of one neuron to this neuron. It is going to trigger opening of the calcium channel. Normally, when there is no nerve impulses, the calcium channels are closed. But when any nerve impulse is going to strike this neuron, there is opening of the calcium channels, which is going to cause influx of calcium inside the neuron. Due to the calcium entry, what is going to happen? This membrane, due to the in this second step, there is an influx of calcium which is going to cause this synaptic vesicle containing a neurotransmitters to fuse with the membrane of the neuron. This membrane of neuron is going to fuse with the synaptic vesicles, and ultimately in the third step there is going to cause the exocytosis. In the third step, the neurotransmitter within the vesicles stored in the synaptic vesicles are being released by the process of exocytosis. What is the meaning of exocytosis? Exo means release outside the cell. Cytosis means cell. Anything which has been released from the inwards of the cell, inside of the cell, towards the outside of the cell, this process is called as exocytosis. Release of the neurotransmitter from within the cell towards outwards of the cell by the process of exocytosis into the synapse. Synapse means the actual junction which is located between presynaptic neuron and postsynaptic neuron. Okay, then what is going to cause? There is exocytosis of the neurotransmitters. It may be excitatory or inhibitory, and there is a release of neurotransmitters at the synapse. And at synapse, when neurotransmitter is been released, this neurotransmitter is going to bind to the postsynaptic receptor to show its pharmacological or physiological action. The next point, third point, we are going to discuss the transmitter action on the postsynaptic receptor. Now we are going to actually see how the neurotransmitter is going to act on the postsynaptic receptor to show its physiological action. See, the neurotransmitter is going to bind to the receptor. It is called as postsynaptic receptor or postsynaptic membrane. Postsynaptic receptor is present on postsynaptic membrane of the postsynaptic neuron. Then what is going to happen? It is going to cause either excitation of the postsynaptic cell neuron or inhibition of postsynaptic neuron. It can induce a excitatory postsynaptic potential. It is called as EPSP or inhibitory postsynaptic potential. Means either it may have an excitatory effect or it may have an inhibitory effect. Let us see what is actually excitatory postsynaptic potential. When there is any influx of potassium or any cations, when there is any influx of cations, that is positively charged ions, when any neurotransmitter is going to bind, if this is a preganglionic neuron or presynaptic neuron, this is a postsynaptic neuron, this is a synapse. When this acetylcholine or any neurotransmitter is going to bind to the postsynaptic neuron, it is going to either trigger opening of the positively charged ions inside the postsynaptic neuron, or either it may going to cause the opening of negatively charged. It is going to allow the opening of negatively charged channels which is going to favor the influx of negatively charged ion inside the postsynaptic neuron. If there is a increase in the positive, there is an influx of positive ions, it is going to result in the excitation of neuron. Due to the influx of sodium and calcium, the influx of sodium and calcium is going to increase the depolarization. Hence there is an increase in the positive polarity through the fast or slow channels, it may depends, leading to the depolarization of the membrane followed by the potassium influx. This is going to cause the excitation of neuron. This is going to cause firing of neuron due to the activation of action potential on the postsynaptic receptor. This is going to take place inside the postsynaptic receptor, which is present after the synapse. Okay, then or postsynaptic neuron. Then examples of this type of EPSP are glutamate receptors, that is NMDA receptors, N-methyl D-aspartate receptors or aspartate receptors. The next one is the inhibitory IPSP. Okay, in this inhibitory type of neurotransmitter, there is an increase in the membrane permeability to anions. Suppose this is a synaptic vesicle which is going to release inhibitory neurotransmitter. This inhibitory neurotransmitter is going to bind to this receptor, which is a postsynaptic receptor, which is located after synapse. Then this activation of this receptor is going to cause opening of some channels, which is going to allow the negatively charged ions to go inside the cell. When the negatively charged ions is going to go inside the postsynaptic membrane, it is going to cause increase in the negative polarity inside the cytosol of the neuron. This cytosol is going to become more negative, leading to hyperpolarization or excessive polarization of the membrane, which is going to cause decrease in the transmission of nerve impulses, that is lower firing of action potential. When there is any influx of negatively charged ion, there is lowering of the action potential, means there is inhibition or very decrease in the conduction of the nerve impulses. When there is influx of negatively charged ion, it is going to decrease the transmission of nerve impulses. When there is influx of positively charged ion, there is increase in the transmission of nerve impulses. We can see in this diagram also, when there is increase, if this neurotransmitter is excitatory and these channels are going to allow positively charged cations to come inside the cell, the membrane will become more positively polarized and there is an influx of positive charge which is going to cause more positive charge inside the membrane, which is going to trigger the depolarization of membrane. In turn, it is going to trigger the action potential and there will be firing of neurons and there is increase in the transmission of nerve impulses across the neuron. This is what we are going to study. In this, there is a presence of inhibitory neurotransmitter and there is a efflux of potassium which is going to constantly takes place irrespective of the type of the neurotransmitter. Potassium efflux to the through the potassium leaky channels is going to occur, and calcium, the chloride influx, that is opening, there is a influx or inward movement of the chloride ions which is going to take place. So there is a hyperpolarization in the cytosol of the cell, hyperpolarization of the postsynaptic neuron, which is going to cause increase in the negative polarity inside the neuron, leading to the lower firing of the, it is going to lower the firing of the action potential. It is going to decrease the transmission of nerve impulses at the postsynaptic membrane. The examples of the inhibitory neurotransmitters are the glycine receptor or GABA receptor, gamma aminobutyric acid. Then let us see the fourth type or stage of this action potential generation. It is postsynaptic activity. What will happen when any neurotransmitter is going to bind to the receptor located on the postsynaptic membrane? This EPSP is going to generate the action potential. It is going to excite the neuron. It is going to increase in the conduction of action potential, and the nerve impulse conduction is going to cause contraction in the muscle and secretion of gland. As you see, when there is influx of the positively charged ion due to the excitatory neurotransmitter, when this EPSP, excitatory neurotransmitter, is going to bind to the postsynaptic receptor, it is going to open the positively charged ions. It is going to allow the influx of positively charged ions. Here it is calcium. When the calcium is going to come inside the cell, what is going to happen? Okay, when this postsynaptic receptor, here is a postsynaptic receptor. When there is a binding of this excitatory neurotransmitter to this postsynaptic receptor, it is going to cause influx of the positively charged ions inside the cell of the neuron at a postsynaptic neuron. Then what is going to have? It is going to cause excitatory effect, means it is going to stimulate the transmission of nerve impulses. When IPSP, that is inhibitory neurotransmitter, is going to get triggered, it is going to get released in the synapse. It is going to act on the postsynaptic receptor. It is going to decrease the generation of the action potential, and hence the membrane will become more negative. There is inhibition or very slowing down or lowering down of the transmission of nerve impulses. You can see in the diagram, if there is a negatively charged or negative, there is an inhibitory neurotransmitter which is going to bind to this receptor. This membrane is going to allow the negatively charged ions to pass inside the cell or neuron, which is going to cause decrease in the, there is increase in the negative polarity inside the neuron, leading to inhibitory effect, lowering of the action potential, or inhibition of nerve transmission or nerve impulses transmission. And there is a decrease in the nerve transmission and sedation. The patient may have sedative action. Then finally, it is a termination of transmitter action. Now we have seen the neurotransmitter is released in the synapse, but it is having a definite lifespan. It is going to have a definite time span. After some time, this neurotransmitter is either metabolized with the help of some various enzymes, or it may be again going to get reuptake into the presynaptic neuron. This neurotransmitter is going to bind to the receptor. This is a receptor, and this is a neurotransmitter. This neurotransmitter is going to bind to receptor located on the postsynaptic neuron to show its effect. Now this neurotransmitter is going to get locally degraded. There are some enzymes which are present on this postsynaptic membrane. These enzymes may be present in the synapse or postsynaptic membrane, which are involved in the degradation of this neurotransmitter. This neurotransmitter is going to break down, or it is going to get degraded, or if it is not going to get degraded, or some part of the neurotransmitter which is not degraded, it is again going back to the synaptic vesicles present in a presynaptic neuron. This process is called as synaptic reuptake of the neurotransmitter into the presynaptic neuron. There is a synaptic reuptake of the neurotransmitter into the presynaptic neuron with the help of neurotransmitter transporter. There is a transporter. If this is a transporter, when the neurotransmitter which is released in the synapse, this is synapse, again this neurotransmitter is taken back into its presynaptic neuron with the help of neurotransmitter transporter or reuptake transporter back to the synaptic vesicle in the preganglionic or presynaptic neuron. And hence there is a termination of the neurotransmitter action. And finally, again the process is going to activated, that is the coming of the nerve impulses. It is going to trigger the opening of the mechanically operated sodium channels, and finally it is going to trigger the change in the voltage. Finally it is going to activate the voltage gated sodium channels, and the process is going to get continued. That is, this process is called as nerve transmission or impulse generation or transmission of nerve impulses within the neurons or nerve cells. In this chapter we have discussed there is an actual transmission of nerve impulses from one neuron to another through synapse, or from one neuron to the effector organ between the neuro-effector junction. Then thank you. In the next lecture we are going to discuss some more important points related to this topic. Thank you.